Okay, I think I got it ready. Okay, so the final is next Wednesday. Like I said last class, you can come here to take it. You can take it from home. It doesn't matter to me. For those of you who are here in class, just let me know. You need to just talk to me or send me an email when you decide. It doesn't matter much to me how you take it. If you do it at home, I think you guys have both taken all of your tests in here. I just wait for you to log on. I send you a link, log on. When you log on, I email you the exam, and then go to town. Just keep your thing up. I watch you guys, and then send it back to me. A lot of people will write it out on sheets of paper and then take pictures of the answers with the phone and then email that to me. That works great. Or you can just come here and do it. So either way. But if nobody's going to be here, then I'll do it from home. Maybe I'll do it from home. The internet's more reliable here, so maybe I'll do it from here. But yeah, just let me know either way. It's comprehensive. It'll cover everything since the beginning of the semester. 1 or 2 questions per chapter probably. I may have more on the last few weeks, but I haven't made it up yet, so I don't know exactly what I'm going to ask. I don't try to make the test any harder. Actually, some people find it easier, just because I tend to, since I know some of the questions were 2 or 3 months ago, I don't take the super in-depth ones. I look for the concepts that I talked about a lot of different times in here, or really emphasized, rather than the small details that you might forget by now. So I think most people who show up to class faithfully find the final easier. Some people won't, but we'll see. Okay, so we're going to finish up with climate change today, and really what I want to do is sort of link together a lot of things we've been talking about this semester. So this class has been primarily focused on 2 things, water and energy. And water and energy both are fundamental concepts when it comes to understanding climate change. And climate change is just going to be one of these things that as time goes on, especially for those of you who are in your 20s, you're going to see this play out over a lot longer time period than I will. This is something that you will deal with in one way, directly or indirectly. We're already dealing with it indirectly, and it's only going to continue. At some point, decisions are going to have to be made on how we really deal with this when the problems start increasing and spiraling. And that will happen. So we said last class that the climate has always changed. There's no doubt about that. You can just look back through geologic history, the different eras. We've had ice ages. We've had periods between ice ages. We've had periods in Earth history where the temperatures were 20, 30 degrees warmer on average than they are now, and the reptiles roam the Earth. We have times in Earth history when there's very little oxygen in the atmosphere. That really only happened in the last 500 million years when land plants became so dominant. Up until then, CO2 was really rich in the atmosphere. But since humans have been on the planet, CO2, methane, and temperatures have been linked really closely together, and those 2 gases are now rising at an exponentially increasing rate, and it only stands to reason that temperatures are going to follow. That's something that scientists agree on. What we don't agree on is what's going to happen in the future. And that's where it gets really difficult. That's where modeling comes in. And what we'll talk about today are some of the effects and how scientists are trying to deal with that. So just what happens if temperatures go up a little bit? Well, as it turns out, by raising the temperature of the atmosphere, you're not only going to change the temperature of the atmosphere, you're going to change the energy in the atmosphere. And since the atmosphere and the oceans are linked so much together, if you have higher atmospheric temperatures, that means you tend to get higher rates of evaporation off the ocean. But it also means that you get greater rainfall because warm air carries more moisture than cold air. So the processes between the hydrosphere and the atmosphere are something that modern scientists spend a lot of time on. This is one of the biggest areas for future scientists, are these links between the atmosphere, the hydrosphere, the oceans, the groundwater. My daughters getting a PhD right now, and she used to ask me all the time, what do you think is going to be the big area in the future for scientists? And I said, studying the interactions between the atmosphere, the ocean, and surface water. And that's exactly what she's doing. She's looking at groundwater and delta environments. And it's just going to be a more and more important part of the scientific focus in the future. So we know that the oceans, the hydrosphere, and the atmosphere exchange mass. Water moves between the atmosphere and the hydrosphere. Energy moves between the atmosphere and the hydrosphere. But the Earth also interacts with both of these as well. We have gases that escape from the Earth every day. Way down deep in the Earth, rocks are being metamorphosed, changed through heat and pressure. One of the byproducts of this are some gases, including CO2, which move up through the rocks and leak out into our atmosphere. Volcanoes provide gases to the atmosphere as well. The Earth is actually a pretty hot body, so a lot of that heat is escaping through the Earth's surface. There's not enough heat if the sun would burn out for us to keep the environment we have, but there would still be some heat here. And then we have plants that take gases out of the atmosphere, like CO2, use them to build their body mass, and then they die. And sometimes we get great deposits of organic matter that get trapped in the rocks as oil, gas, coal. So we have this exchange of mass between the Earth, the hydrosphere, and the atmosphere. We have energy that moves back and forth. And those are things that are really difficult for scientists to quantify, to put numbers on. And we need to. If we're really going to understand how much humans are affecting this, we also have to understand how much nature is affecting all this. And a lot of these topics are pretty difficult to deal with, and we're just starting to understand them today. As I said a second ago, the Earth would still have some warmth even if the sun wasn't here, but it wouldn't be enough to sustain life as we know it. So we rely on energy from the sun. And we've been studying the sun in detail for well over 100 years. And the energy from the sun goes up a little, down a little, up a little, down a little, depending on solar activity. But for the most part, it has been a very stable feature, providing us with a stable amount of energy. The amount of energy we're getting from the sun isn't increasing. It's not decreasing. It's just staying rather constant. And that's good. That's easy for us then as scientists to sort of set that aside. It's like, well, the sun's not doing anything different, so things are changing in our atmosphere. We can start looking elsewhere. So what we'll spend the rest of the class on is looking at how mass and energy cycles between these spheres, the atmosphere, the hydrosphere, and the geosphere. And then take a look at whether humans can affect this process enough to matter. There's a large segment of our population that simply doesn't believe that humans are powerful enough as a species to have any great effect on something as large as the Earth and its atmosphere. Again, I think if they lived in China, they would probably have a different opinion, because you can definitely see how human activity is affecting the atmosphere there. For those in the US and other developed countries where they have much cleaner air and water, we don't see those effects so easily. They're sort of invisible to us. And I think that makes it harder to really come to grips with. Okay, so a couple concepts. And we've talked about these a little bit, but I don't think I've ever kind of thrown them out here in notes and really talked about them specifically. So to understand how the atmosphere works, there's just a couple basic concepts that if you understand them, then it's much easier to sort of envision in your mind how the atmosphere is going to respond to things that humans might do to it. So this first concept, warm air rises and cold air sinks. Warm air, because the molecules are vibrating more and taking up more space, is less dense. These atoms move, they take up more space, there's less of them in a certain volume of air. That means its density is lower and warm air will rise. And conversely, cold air will sink. And what you end up getting are circulation cells in the atmosphere, where warm air rises. As it rises, it cools, it becomes more dense, and then it sinks. And as it sinks, it warms up. Its density lowers, and it rises again. So it cools as it rises, and then it sinks back down, and as it sinks, it warms up, so it rises again, and you sort of get the cycle where air is continually rising and cooling, and as it cools, then it sinks, and as it sinks, it warms up, as it warms up, it starts to rise again. The other thing is that cooling will cause water in the air to condense. Warm air carries more moisture than cold air. So what that means is when the air cools off, it can't carry as much water and has to get rid of some of it. And it does that as small water droplets. And these small water droplets adhere to any sort of little particle that might be up in the atmosphere, a little speck of dust, an aerosol emitted by a volcano. So warm air rises, cold air sinks. Warm air carries more moisture than cold air. So cooling will cause water to drop out of the air mass as little water droplets and eventually rain or snow. Now our atmosphere is either ridiculously simple or enormously complex, depending on how you want to look at it. If you take the big picture, almost 80% of our atmosphere is nitrogen. Simple nitrogen. 21% is oxygen and 1% is everything else. If you look at it from that standpoint, it's pretty simple. Our atmosphere really consists of two main gases, nitrogen and oxygen. Now, as it turns out, though, that 1% is not something we should ignore. So if you start looking at that 1%, then suddenly the understanding of the atmosphere gets much more complex. Because that 1% is extremely important in how our atmosphere behaves, how much energy it contains, how it affects ecosystems. And the reason that 1% is so important is that 1% contains what we call greenhouse gases. And that's any gas that has a high capacity for retaining heat. And there are lots of different greenhouse gases. We always hear about CO2. That's not the only one. In fact, water vapor is a greenhouse gas. Carbon monoxide is a greenhouse gas. Methane, as we talked about last class, is a greenhouse gas. And we're going to talk a little about feedback in a minute, but this is probably a really good place to show one potential feedback. So we said that this gas right here, water, is a greenhouse gas. It'll make the atmosphere warm up. Now, if the atmosphere is warmer, what does that do to evaporation rates? Jacks them up, right? So that means that even more water gets into the atmosphere. What does that additional water do to the temperature? Raises it up. What's that going to result in terms of evaporation? More evaporation. So you get more evaporation, more warming, more evaporation, more warming, more evaporation, more warming. So that's one of those feedback cycles that scientists are really concerned about. We see that with methane right now as well. There's lots of methane in polar regions that have been trapped beneath the permafrost. When the permafrost melts, methane goes into the atmosphere. If methane goes into the atmosphere, what happens to atmospheric temperatures? They warm up. What happens to the amount of ice that melts? More of our permafrost melts. What does that do to the amount of methane? The amount of methane goes up. What does that do to warming? Another one of these feedback cycles. And what scientists are rightly concerned about is if we get this process started in one direction, how do we stop it? If all these things are just going to ultimately make the problem much worse. Will we ever get to a point where we can't rein it back in? Some people think we're already there. I think most scientists think we have a little more time to get this under control. I mean, if you look back over the last 500,000 years or so, we've had 6 ice ages. CO2 levels have gone up, and then for some reason they've gone back down. So there's clearly some way that nature in the past has managed to rein this in. Can we as well? Or do we end up like the planet Venus, where it just ran out of control and now the whole planet is covered in CO2? The surface temperatures are hot enough to melt lead. Venus is an interesting case. It's warmer. Some people say, it's closer to the sun. It is. But scientists have been able to determine if you took Earth and you put it into Venus's orbit, it would be warmer, but it'd only be 40 or 50 degrees warmer. The surface temperature on Venus right now is 500 degrees centigrade. That's hot enough to melt lead. You don't want to live there. So it's much hotter because its atmosphere is almost all CO2. We don't want to get to a place where Earth becomes like Venus. Well, this goes back to the feedback thing. What if the percentage of greenhouse gases in our atmosphere increases? That means that the heat retaining capacity of our atmosphere increases. In other words, it should warm up. Now, sometimes we have feedbacks that go the other way, though. So think about it this way. So if warming atmosphere causes more evaporation, that means there's more water in our atmosphere. Shouldn't that also mean that there's more clouds in our atmosphere? And if there's more clouds, what does that do to the amount of sunlight that can get through to the Earth?
Isn't it like reflected off?
It reflects it back out into space. So that's negative feedback. It's like, hey, maybe this thing will sort of fight itself as well. So we have positive feedbacks, like more evaporation leading to, or more permafrost melting leading to more methane, leading to more heat, leading to more melting, leading to more methane. That's a positive feedback. Negative feedback is warmer temperatures, more water in the atmosphere, more clouds that will reflect the sunlight and actually lower the temperature. So we have to somehow come to grips with, okay, what are our positive feedbacks? What are our negative feedbacks? Which one's going to win in the future? Right now, all the best science says the positive feedbacks are going to outweigh the negative feedbacks. It's not going to cancel itself out. People are still working on this, and like I've said a few times in this class, the one thing about science is it may not give you the right answer every time, but as time goes on, you get closer and closer to that right answer. And that's what's happening with our understanding of climate change. So yeah, we don't know everything there is to know about climate change. But everything that we do know right now suggests that we really need to take some actions pretty soon as humanity, or we might get on one of these positive feedback cycles that we can't rein back in. 5 years from now, we'll understand this a little better. Maybe things will change in what we expect the future to be, but maybe not. But we'll get closer to the answer as time goes on. So there's lots of questions that scientists are looking into. Because a lot of things affect the temperature of the Earth. You guys probably know this from the summer. Nice, hot, sunny summer day. You got a black car and you got a white car. Which one do you not want to put your hand on if it's been sitting out all day? The black one. Different colors reflect or retain the sunlight differently. And the Earth has a color. If you go to the poles, it's white. That means it's reflecting a lot of sunlight. If you go to other areas, it's really dark with plants. So what if the amount of plants on the Earth increases? What if we get lots of melting of the poles, and where that material melts, suddenly we have plants? Well, you change the color, right? You go from white to dark. It should warm up. But what do plants do? What's their daily routine? Yeah, which means they suck CO2 out of the atmosphere, which should bring it down. So you have these two effects that they sort of play against one another. So what scientists need to do is let's figure out how much. You know, how much cooling will that sucking up of the CO2 create versus how much warming will the loss of ice create? What if we put more CO2 in the atmosphere because we have a bigger population on Earth and more people want access to affordable electricity? The big one, this is where lots of research is being done right now, is what's going on with the oceans. One thing that's happened that scientists didn't expect to happen to the degree it has is that the oceans have warmed up. We knew they would warm up. If you put an ocean against a warming atmosphere, it should warm up. But the oceans are warming way faster than people thought they would. That's one of the reasons why the hurricanes in the Gulf of Mexico are getting so big, is that the Gulf is getting so hot so fast. And that warm water really fuels the growth of large hurricanes. The other thing is if you warm up the water, you also create more things like algae. Remember, most of the Earth is covered by water. If you warm up the oceans, you increase the algae. Algae are photosynthesizing plants. So they're sucking CO2 out of the ocean water. That means the ocean water can suck in more CO2 from the atmosphere. So maybe that'll help things out. So each of these things that I've listed up here has to be studied individually and then compared to all the other things that are going on around it. So I have this whole thing that says, what if, what if, what if? That comes down to looking at each of these little parts, coming up with mathematical models to determine the amount of effect that each of these will have, and then comparing all of them. So there's really two ways that scientists are dealing with what's going to happen in the future. One way is to look at the past. We can see in the past that when CO2 levels are low, temperatures are low. When CO2 levels are high, temperatures are high. So we can expect that if we change the gases in our atmosphere, we're going to change the temperature and we're going to change the way life on Earth responds to it. But that doesn't provide us with values, with the amounts. And that's where mathematical models come in. That's why in science we always have our students learn lots of math, because modeling becomes really important. Models don't tell us exactly what's going on in the future. The better the model is, the closer it will come to reality. But it does give us some ideas of what might occur so that we can study it in more detail. Here's a little look at our atmosphere, okay? It's kind of a busy diagram, but I'll try to break it down into a couple of pieces. So we live down here right on the Earth's surface, right here. This is where we are. The air that we breathe every day is a part of the atmosphere that is called the troposphere. Troposphere is the layer of atmosphere that's closest to the Earth's surface. Up above the troposphere is the stratosphere. There's two spheres above that, and we're not going to worry about that in this class. You can take an atmospheric science class, and you can worry about what's going up here in the mesosphere and the thermosphere, but we'll just ignore that. As it turns out, there's not a lot of air up there. The air is ridiculously thin. What we're going to concentrate on is the troposphere and the stratosphere. The troposphere goes up to about 30,000 feet or so. Varies a little bit from place to place, time to time. It's around 30,000 feet. Mount Everest, if you go to the top, you are kind of right near that boundary between the troposphere and the stratosphere. That boundary is called the tropopause. Now this is going to be a little harder to understand, but a couple things that you know that should help you with this. Down here where we are in the troposphere, as you go up in elevation, as you go up into the mountains, what happens to temperatures, air temperatures generally? The higher you go, the colder it gets, right? So you go to the top of Mount Everest, it's just damn cold up there. So if you have warm air here at the surface, okay? It's warmer than the air surrounding it. We already talked about warm air is less dense, right? So it's going to rise, right? As it rises, what's happening to the air around it? It keeps getting colder, right? So warm air is going to keep rising, right? Because it keeps encountering even colder and colder air. It's just going to keep rising. Up until where, though? See what happens in the stratosphere? Look at this red line right here represents what's going on in the stratosphere. In the troposphere, as you rise up, the temperatures drop. Right? You can see this. I'm going to need a different color here. All right. Let me get rid of all this junk. Let's do this one. So here in the troposphere, as you rise up, temperatures drop. Right? What happens in the stratosphere? Temperatures rise as you go higher. So what will happen is a warm air, it'll rise completely through the troposphere because it always encounters colder air above it. But then what happens when it hits the stratosphere? It's going to find some warm air, right? Can it keep rising if it encounters air of the same temperature around it? So it stops. It stops rising. And that's where the term stratosphere comes from. Strata, it's where the air just sort of lies flat. It doesn't want to rise, it doesn't want to sink, it just sort of stays at the same level. So what that means is down here in the troposphere, we have air rising and cooling and dropping and rising and cooling, and we get lots of circulation. It's very well mixed. In the stratosphere, it's not well mixed at all. You get layers of things. So the troposphere, where we are, tends to be important to understand. The circulation keeps it very well mixed. And this is where our weather develops. This is where we get thunderstorms, rain, snow. One of the interesting layers in the stratosphere that we don't have in the troposphere is something called the ozone layer. I know this is something you've all heard of. Ozone layer. Ozone layer, ozone is O3. You guys breathe O2, okay? Ozone is O3. It's 3 oxygen atoms that are hooked together. And it forms in response to sunlight. It's a process called photodissociation, which means photo or light breaks apart an O2 molecule. Remember, there's lots of oxygen in our atmosphere. So if a sunlight ray hits it with enough oomph, it'll break that O2 into 2 oxygens. And then each of these oxygens then float around until they bump into something. If they bump into another O2, they can form O3. And that tends to happen in this layer right here up in the stratosphere. So we get ozone that forms in that layer because of sunlight. And one thing that ozone does is that it's good at filtering out radiation that comes in from space. We know the magnetosphere does that, but ozone does it as well, and it really works well on ultraviolet light. That's one of the things that absorbs really well. Now, as it turns out, it doesn't absorb enough light to really affect temperatures. So the ozone does really not play much into our conversation of climate change. But it's still really important for us. You may have heard of the ozone hole. It's not really a hole. It's just an area where there's no ozone forming. And there was a really big one over Antarctica for many, many years. Actually, it's likely that the Earth has probably always had ozone holes over the poles. Why would you get an ozone hole over the pole? Think about sunlight. What happens for 6 months a year at each of those poles? They go dark, right? Yeah, we're going to point right now that if you went up to our North Pole, you're not seeing the sun. You're not going to see the sun till March. So is there any ozone being created? No, so there's a lack of ozone over the poles. Well, what happened though is that these ozone depleted areas or holes just started growing and growing and growing. And in fact, the one in the southern hemisphere got so big that it covered Australia. And if you don't have ozone, then you have lots of harmful ultraviolet light coming in that wouldn't have come in before, and that spikes skin cancer rates. And they found out that one of the things that eats ozone is something called a chlorofluorocarbon. It's not important that you know this, but it's what they used to make aerosol cans out of. You know, the spray, that used to be CFCs, chlorofluorocarbons. And they go up into the atmosphere, they stay up there 20, 25 years, and they just eat ozone. That's all it does, is it just eats ozone. So back in the, I think it was late 1980s, there was a worldwide ban on CFCs. All the countries got together and said, we're going to stop using this. Freon that they used to put in air conditioners, loaded with chlorofluorocarbons. That's why today's air conditioning maybe doesn't work as well as the stuff in the past because they had to change it. The stuff worked really well, but it also put a lot of CFCs into the atmosphere, which ate a lot of the ozone. Well, since we stopped putting ozone in the atmosphere, those holes have gotten much smaller. So there's one example right away of where humans are affecting the atmosphere in a huge way. You can't see it, but now the skin cancer rates are going down in Australia. The ozone holes are much smaller. And it's because the world actually got together to do something good for the environment, which is pretty rare. We have a hard time agreeing as humans on what we should do sometimes, but in this particular case, everybody was on board and said, yeah, we're going to ban this stuff. We're going to have to make some adjustments, find other things to put in aerosol cans, put other things to put in air conditioners. And they have. And the ozone rates are much better. The reason I bring this up is simply to show that humans can affect the atmosphere in a big way. We can affect it for the worst, but we can also do things that can bring us back to a more normal state. Talked about this already. The stratosphere is warmer than the troposphere. That means that rising warm air will eventually encounter air of the same temperature and not rise anymore, and then just spread out. The flip side to that is that we're kind of stuck with our air down here. It rises and it falls, and it rises and it falls, and the stratosphere keeps it from rising too high. That means if we pollute the troposphere, it just keeps coming back to us. It doesn't go up into the upper reaches of the atmosphere and stay there. It rises up a little and then it comes right back down. So when we talk about affecting the atmosphere, we're really talking for humans about what are we doing to the troposphere. It's where most of the atmosphere by mass is, and it recirculates. It's kind of like the recirculating air in your car. You put something stinky in your car and put on the recirculate, you just get stuck with that all day. If we pollute our troposphere, we get to keep dealing with the troposphere. So again, humans live in the troposphere. If we mess it up, we're stuck with the air that we mess up. So again, this is kind of going against that prevalent misconception that humans can't affect the atmosphere to any great extent. We certainly can. And one of the reasons why we can is we're stuck in the troposphere, and the troposphere is stuck with us. Because this air down here that's really low, it just keeps getting recycled. We don't access much of this air up in the upper parts of the atmosphere. Okay, I always found this part interesting when I learned it back when I was a college student, about circulation patterns here on Earth. It goes back to some of those concepts I told you about a few minutes ago. The idea behind it's really simple, is that warm air rises and cold air sinks. Where do we tend to get the coldest air on the Earth's surface? If I said, go somewhere cold today, where are you going to go? The poles, right? Yeah, so you tend to get cooler air at the poles. That's where air likes to sink. To get air to rise, you got to warm it up. Where would you go on Earth today if you wanted to warm stuff up? Go down to the equator, right? Where it gets the maximum amount of sunlight. So what we tend to get is air rising at the equator and dropping at the poles. And if you look at the areas along the equator, they're very rainy. Because what happens is warm air that carries a lot of moisture rises. As it rises, it cools. As it cools, it condenses, and it rains. So where you have rising air, you tend to get rainforests. When cold air descends, as it descends, and remember it's cold, so it's dry. Okay, so it's starting out really dry in the upper atmosphere. What happens is it descends, it warms up, right? It's already dry and now it's warming. And remember, warm air can carry more moisture than cold air, so what it does is it basically sucks all the moisture out of the environment. You get really high evaporation rates where you have cold air that descends. By the time it reaches the Earth's surface, it's warmed up and it actually can be quite hot. But it's super dry. And if you go to the poles, even though they look snowy and icy, they're actually deserts. They get very little precipitation, very little snowfall. Just that when it falls, it stays because it's cold. Antarctica is a desert. It's one of the driest places on the planet. There are some places in Antarctica where it has never rained or snowed in human history. It's just that dry. As it turns out, our circulation is a little more complex than that. Air rising at the equator and sinking at the poles. As it turns out, the air that rises at the equator can't travel all the way to the poles before it sinks back to Earth. And what we end up with are actually 6 big circulation cells on Earth. 3 in the northern hemisphere and 3 in the southern hemisphere. And we call these Hadley cells. I'll show you what they look like here in a second. And these things are great because it really explains a lot of the climates that we have here on the Earth's surface. Give you a second to get your notes done. Okay, here's what Hadley cells look like, okay? So it's a little messy, but I'll break it down for you. So we got the Earth underneath here. So let me see, what would be a good color to use? Not red, not green, I'm gonna use purple. Okay, so here's the equator right here, okay? There's the equator. We said the equator was where the Earth's going to get the maximum amount of sunlight, maximum amount of warming, and you should get rising air, right? And that's what this is showing right here, is that you're getting rising air right over here. Okay, so what happens is on the equator, the air rises. As air rises, it cools off. As it cools off, it condenses, and you get lots of rain. So right here along the equator, that's where we get most of our rainforest. Look where the equator crosses South America. Right here, what do you have there? You have the Amazon basin, one of the greatest rainforests on the planet. That's because air is constantly rising, okay? So it rises, it cools, it condenses, rain falls back to Earth, you get wonderful rainforests. And then what happens is that air now has dropped all of its rain and it's rising, so when it's up here, it's now cold and dry. What's going to happen to cold air? It's going to start to fall back to Earth, right? So that happens at about 30 degrees north and about 30 degrees south. Okay? As that cold air, the cold air is dry, right? As it descends towards the Earth, what's going to happen to its temperature? It's going to go up. It's already dry, and now it's getting hotter. So it wants to just suck water out of anything, because warm air can carry a lot of moisture. So it sucks all the water out of the environment. And sadly, I can't turn this globe, but if you go over here to Africa at 30 degrees north, guess what you have there? You get descending air. That's where your Sahara Desert is. And down here, you have the Atacama Desert. If you go over to Africa, 30 degrees south, you have the Kalahari and the Namib Desert. Most of the world's deserts are found 30 degrees north and 30 degrees south, where you have this descending air. So then that air travels across and it warms up, and at about 60 degrees north and 60 degrees south, it rises again. As it rises, it cools off. As it cools, it rains. So what you end up with are temperate rainforests that you get up in British Columbia, southern Alaska. If you go down here, you go way far south, into South America, you get some of the rainforests that are down in Patagonia. So that air is now rising. Once it rises, it travels. When it gets to the pole, it descends. it warms a little, it doesn't have any moisture, so you get deserts at the poles and at 30 degrees north and south. And rainforest you get at the equator and 60 degrees north and south. Wherever you have rising air, you get rainforests. Wherever you have descending air, you get deserts. And if you look at a map of the world, which I don't have up, but you can see that most of the world's great deserts are at the poles and at 30 degrees north and south. There's a better map. I did have one. So here's the equator right here. Rainforest. Sub-Saharan Africa right here. Super rainy place. Go to Indonesia, Philippines, Southeast Asia. Super rainy place. Amazon Basin. Super rainy place. 30 degrees north. We have the Sonoran Desert. We have the Sahara Desert. 30 degrees south, we have the Atacama Desert, the Kalahari, the Namib, and look at Australia. We already know Australia is a great desert and sits right at 30 degrees south. And then the polar regions again down here, deserts, deserts, and then 60 degrees right here, we have temperate rainforests on the coastline. Over here we have some deserts that are up in there, but they're behind mountain ranges, what we call rain shadow deserts. And then 60 degrees south down here. So you can explain a lot of the Earth's ecosystems by these Hadley cells. Okay, we're going to finish up with oceans. Just a few minutes on oceans. Oceans are something we should teach more and study more and understand more. Because most of our Earth is covered with it. It's where a lot of our food could be extracted from. It's how most of our weather patterns are affected by ocean cycles. So let's just start with, you don't have to write this down, but this is just what we call the hydrologic cycle. Remember, most of the Earth's surface is covered with ocean water, so we get lots of evaporation off the oceans. That water vapor goes into the atmosphere. Sometimes it condenses as clouds. The clouds can move inland, where you get rain and snow. Some of that soaks into the ground, where you get groundwater flow. Some of it runs across the surface as streams. Some of it evaporates back up into the atmosphere. All this cycle is showing is that water moves around a lot on the Earth. It moves around a lot in the oceans because we have ocean currents. And then when it evaporates off the surface, it can come inland and replenish groundwater stores, glaciers, lakes, rivers. We know that the ocean is salty. And it appears that the ocean's saltiness has been relatively stable for a really long time. On average, ocean water contains about 3.5% salt. And it's not just NaCl table salt. There's a lot of other things that are dissolved in there too. There's some magnesium chloride, some sodium sulfate, calcium chloride. There's dozens of different salts. But the vast majority of it is NaCl, sodium chloride, table salt. So if you just go out in the open ocean, it's about 3.5% salt. Now some places, like the Persian Gulf, it can get as high as a little over 4%. And that's because you have massive amounts of evaporation because it's really hot there. And it's kind of a closed off part of the ocean. It doesn't have a lot of exchange with the larger ocean. And then some places it's a little lower. Like in the Baltic Sea. It's only about 2%. And the reason it's so low is that they have so much fresh water pouring in off the land surface that it's diluting it a little bit. So you got areas that are a little less than 3.5, some areas a little more, but the vast majority of the oceans are about 3.5% salt. Now, where does this salt come from? Well, as it turns out, it actually comes from the rocks. When the rocks here on the continents erode, let's say we have rainfall, lands on the rocks, some of those rocks dissolve slightly, and some of that dissolved material goes out into the ocean. Some of those dissolved materials can be used by ocean life as nutrients. But a lot of it doesn't, so it accumulates in the ocean water. And some of it will settle out into the ocean floor. And we're kind of in a steady state right now where we're adding about 2.5 billion tons of stuff to our oceans a year, but about 2.5 billion tons of stuff falls out of the ocean every year. So it's staying relatively constant with its salinity. So the origin of salt is the rocks on the Earth's surface. What's interesting is one of the first attempts to figure out how old the Earth was by the saltiness of the Earth. It was assumed that at first, when the Earth first formed, that the ocean would have been clear of salt. And then they started calculating how much salt is added every year. And when they did that, they came up with about 100 million year old Earth, which isn't very old geologically. And the reason that it didn't work is that the ocean got to a point where everything that was added just dropped out into the seafloor. So it stopped getting more salty. If it had kept getting more salty, we would have come up with a better estimate, but it just didn't work that way. So again, most of the stuff comes off the continents. Volcanic eruptions contribute to this immensely. And if you're adding 2.5 billion tons of material a year, why is it constant? It's because some of the stuff is removed at the same rate. Plants and animals, or it settles out in the seafloor as a precipitate during evaporation. So again, we're just at the steady state where our salt concentration is going to be about 3.5%. We keep adding to it, but then plants suck up some of this and some of it falls out to the bottom of the ocean. So it gets removed at the same rate. And the result is that our ocean saltiness hasn't changed much in a really long time. And unfortunately for us as humans, it's a little too salty for us to drink. And I think I have a slide coming up about what humans can tolerate in terms of salt water. I think we'll get to it. The other thing is that ocean waters aren't just, it's not like a big lake where it's just a big stagnant body of water. Ocean waters move very rapidly and it moves a lot of water. This North Atlantic current that you see here, it has greater flow than the Amazon. And it's a warm water current. So what that means is it brings warm water to places like England. If this current didn't exist, England, Ireland would be much colder. In fact, England and Ireland are at the same latitude as Juneau, Alaska. And the weather is very different. Alaska is much colder. And the reason that the UK is much warmer is simply because they have this current right off the coast here. So these currents greatly affect the land temperatures next to where these ocean currents flow. This is one thing I wanted to talk about is El Nino. because I think we're in a La Nina year right now, I believe, which is a period between El Ninos. El Nino, a lot of people have heard about it. All they know about it is that, it does something to our weather. It's true. But what it really is, it's a change in one ocean current. So normally, our ocean, and this is the Pacific Ocean right here, there is a current, and it's hard to tell, but this is North America right there. So it's just showing the Pacific Ocean. So South America is right here. So what this is that this is a current that tends to bring cold water to the west coast of South America. And that's really important. Cold water is what you want in your ocean if you're concerned about the number of fish and bird life. Cold water is what most fish species prefer because it has more oxygen and it has more nutrients. Cold water is the bomb. That's what you want. And because of that cold water, the fishing off of the west coast of South America is generally really great. Go to places like the Galapagos, it's just teeming with ocean life because of that cold, oxygen-rich, nutrient-rich water. So that's the normal situation. But every 3 to 8 years or so, and nobody knows exactly what the reason is, instead of a cold water current moving across the Pacific, we get El Nino years where warm, I'm gonna have to change my color here, where warm water moves over. And as you can imagine, that warm water has less oxygen, less nutrients, and it destroys the fishing. That's what was first noticed, was the effect on the fisheries. But you can see what happens is there's kind of a ripple effect. Look up here off of the west coast of North America. During regular years, we have nice cold water up here, right? Look at during El Nino years. Nice warm water up here. That's definitely going to affect the weather up here. So it tends to affect the weather. Not always in a predictable manner. Some years were super snowy and some years were not during El Nino years. So El Nino, when you hear about it, it's just a change in this Pacific Ocean current. Normal years, you get nice cold water, great fishing off of South America. During El Nino years, water gets really hot. And we just don't know exactly why that occurs. Again, these warm waters show up every 3 to 8 years, about this time of year. As I said before, I think we're in a La Nina year. I don't think El Nino is happening this year. They usually can predict it a couple months out. And these things typically last for several months. One thing we don't know is what's going to happen to El Nino if we have continued climate change. There's been some studies that have come out that says if we keep warming up, El Nino goes away. Kind of. I don't know. Yeah, there's been models that have been trying to deal with this. At this point, they're very conflicting. We will get better at this. But that's one thing that warming temperatures might change. So again, this is basically a reversal of current. They think the current reverses because the winds die down. And they don't know why the winds die down yet. So it's still something that's that warrants a lot of study. I think I'll just end it up with here. You know, we do know that El Niños affect especially the area where the current changes direction. You get warm water in places where you usually have cold water. That warm water carries less oxygen, so fish die. When you have less fish, you have less food for birds and other wildlife that depend on the fish. We know it affects global weather. Some areas get much drier. Some areas get much wetter. They've noticed increase in malaria during El Niño years, where you get places that get flooded because of the increased rainfall, leading to more mosquitoes, leading to more malaria. So it can even affect health. Again, we don't know why. We do have evidence that El Niños have been around for at least 5,000 years. We don't know if they were around during the last ice age or not. And we don't know whether climate change is going to give us more El Niños, less El Niños, stronger El Niños, weaker El Niños. Warmer temperatures are likely to affect it, though. And what that means is we're going to have a changing Earth. So again, the punchline is, we know the climate's changing. We know humans are partially responsible for it. We don't know what the future effects are going to be. We just know it's going to be different. It's probably going to be costly. And not only in terms of economics, but maybe politically, stability-wise. More people are going to be forced to move. That can lead to wars. We don't know how this is going to play out. It'd be better if it wasn't. A stable Earth is something we can rely on. A changing Earth, that always makes things more difficult. All right, well.